Good afternoon. My name is Brian Pailes. I'm with Vector Corrosion Services. Today I'll be giving a presentation on corrosion assessment of parking garages. I'm a professional engineer and a NACE cathodic protection specialist, extensive experience in the field of non-destructive testing, material testing, structural evaluation, and corrosion assessment of reinforced concrete structures. I have my Ph.D. from Rutgers University, master's from the University of Virginia, and my bachelor's from Northeastern University. And also I have a certificate in engineering geophysics. So like I said, today I'll be talking about the corrosion assessment of parking structures. So, talking about professional services to extend the life of building and parking. So we're not only parking, but buildings is going to be included in this. So looking at kind of understanding the cause and effect of reinforcing corrosion, methods to identify the magnitude and extent of that risk, and kind of how, talking about different destructive and non-destructive methods. So I always like to start off my presentation by talking about, kind of what is it that we're really looking at in a concrete structure. And so here on this screen here, we have a large near surface delamination. And so you can kind of see here, we've gone and hammer sounded this structure, and the white hatching is where there is a large near surface delamination. Now that is obviously concrete that is debonded. There's corrosion activity there. It's going to cause deterioration and fall off. But is that the only thing that's happening there? Well, we probably have delamination and debonded concrete that extends beyond that white hatched area, right? If we took a chipping hammer to that white hatched area, we all know that it's probably going to grow in size because there's areas of that damage area that we can't identify with hammer sounding alone, right? There's micro cracking and smaller delaminations that exist beyond that white hatched area that when we take, a chipping hammer or something physical to it, it's going to open up. So if we just went with the quantity of area that was identified by the white hatched area, we're probably greatly underestimating the proper repair area. And then in the end of the day, it's probably going to end up being the white area and that yellow area. But if we just go out and repair the white and the yellow, are we really addressing the structure fundamentally? Could there be areas of corrosion beyond that repair area that are active but have not formed enough iron oxide to cause cracking or delamination of the concrete? So this red area represents potentially areas where there's active corrosion, but that corrosion is pretty young. And so it hasn't created enough damage yet to be really necessitate a repair. But if we only go out and repair the yellow and the white, are we really preserving the structure for the long term? Or will we have to come back in 5 years and repair that area in the red as well? So that's kind of what I'm going to be talking about today is kind of the corrosion and how it affects deterioration and evaluation of that corrosion. So a little bit of background on corrosion, just so we can get everyone on the same page. Corrosion is an electrochemical reaction. So we have the anode, which most people are very familiar with, where iron becomes iron oxide. So iron loses an electron. So that's where the rust occurs, the red rust. And so effectively what's happening is iron's becoming iron oxide, we're losing that electron. But when we lose an electron, we have to gain an electron somewhere else. And that's the cathode part. So that electron travels to the cathode, combines with oxygen and water, and creates hydroxyls. And so the cathode, there's no suction loss occurring there. It balances out the anodic reaction. And because we have current flow between these two, we have to complete the circuit. And so we have ionic current flow through an electrolyte, which in this case is concrete, but an electrolyte can be soil or water as well. So this is the basic corrosion reaction. And if we take away nothing, really the important item here is that the anode is where the rust forms, where the section loss occurs, and the cathode, there's no section loss. So obviously a source of corrosion is chloride induced corrosion. So chloride ions penetrate into the concrete, destroy the steel's natural passivity, causes corrosion. Typically these chlorides can come from marine environments, de-icing salts, chemical processes. Sometimes they can get cast into the concrete. So once the chlorides reach the steel, break that passivity, there's no going back. They're not consumed in the reaction. So once they break the passivity and allow corrosion to occur, then corrosion can occur unabated. Another source of corrosion is carbon dioxide, carbonation of the concrete. So concrete will absorb carbon dioxide from the air, And as it does, that carbon dioxide will react with the free lime and lower the pH of the concrete. So here we have a concrete core with a pH indicator solution sprayed on it. And you can see the pink area is where the pH is high, and the clear area here is where the pH is low. So that carbonation front is reached to this boundary here. If the rebar is within that clear part, then corrosion can occur of that steel because the pH has been lowered. If the rebar is still in the pink part, then we don't have corrosion, but obviously we have risk that that front is going to continue to move forward. We often see carbonation when concrete permeability is very high. So if the concrete is very permeable, carbon dioxide will permeate into it very quickly. Industrial sites where you have a lot of emissions, carbon dioxide and monoxide, that can cause carbonation quicker. And also very old structures. Carbonation is just a matter of time. So as we move through time, carbonation keeps occurring on all structures. So historic structures tend to have this issue much early. Very old structures will eventually have this issue. So with corrosion of reinforced concrete, what is really causing the damage? The damage is really the result of iron becoming iron oxide. So iron starts to grow in size. It's an expansive product. So as iron becomes rust, iron oxide, it grows up to 6.5, 7 times its original size. So it's a very expansive product. And so if we have an expansive product inside concrete, that expansive product will crack and delaminate concrete and cause spalling. And so that's really what's causing the damage of the concrete due to the steel corrosion. So for conventional reinforcing steel, typically we see things like this column here where we get a spall, we have some rebar corrosion, and that's an indication to most engineers like, hey, we need to start addressing this structure, right? We've got some damage that's observed. Typically, we're going to see these kind of spalls occur before anything structural is a matter with this element. So obviously, we have some section loss and some deterioration, but from a structural point of view, we're probably not very worried about this column. However, with high strength tendons, so precast post-tension elements, we can have significant section loss without a lot of concrete damage. So here's a pre-stressed beam on the bottom here, and we can see that once the spall has formed, the strands are completely broken. So in order for enough corrosion product to be formed to cause the spall, there was such high section loss of those strands because they're so small and under a lot of stress, you don't create as much iron oxide as you would with a conventional bar. So by the time enough iron oxide was formed to create a spall, we have very significant section loss of the steel, complete breaks of those strands, and clearly we now have a structural issue with that element as opposed to with conventional steel. So if we're waiting for the same visual indicators to identify when we need to address a pre-stress or post-tension element as we would a conventional bar, then we're probably waiting too long. So with those elements, we probably need to do evaluation and mitigation much sooner in their visual condition than we would with a conventional rebar. So what are some methods that we can use to better understand the condition of various structures? Well, a lot of what I'm going to talk about today is kind of different evaluation methods, not some destructive, some non-destructive. But here we have kind of a structure condition over time. And, at a new structure, it's great condition. And then over time, the condition deteriorates, and typically deterioration is exponential. So you get more and more deterioration with time. The typical methods that we use, hammer sounding, train drag, and visual inspection, these really identify late stage deterioration, right? Chain drag, hammer sounding can only find delaminations when they've become large and near surface. So they're kind of late in the delamination phase. Or, visual inspection when we start to see spalls and surface cracking and things is pretty late in the damage stage. But there's other parts of that phase, right? So we start with chloride and moisture penetration. We then move on to corrosion of the rebar. That rebar starts to grow, causes cracking, and then delamination, and then spalling. So if we use things like impact echo, we can better identify delamination sooner than, say, with chain drag. Ground penetrating radar can identify a lot of different conditions, and so we can identify maybe rebar corrosion with, say, half cell or GPR or chloride and moisture penetration with some of these other methods sooner so that we can address the condition before it gets to delamination. In addition, all of these conditions are happening simultaneously on a structure. So if we go out and look at a structure and we find a delamination, well, there are other areas of that structure that are probably rebar corroding without delaminations. There's probably areas that have some chloride and moisture exposure that haven't started to corrode. So all these conditions are happening simultaneously on a structure. So if we just identify where the delaminations are we really understanding the true condition of the structure? And are we really rehabbing it or extending its service life to an effective way if we don't understand where those other conditions are? So I'm going to start talking about some project histories here. So the first here, this is a parking garage in Washington, D.C., where we did a corrosion assessment and repair and corrosion mitigation too. This parking garage is 6 floors underground. So the top floor is at grade, and then the next 5 floors are below grade. It's got this 2-bay split level design, so it's kind of like a half level down is the next level. It's cast in place reinforced concrete, and it obviously, in Washington, D.C., the exposure here is due to de-icing chemical application on the roadways in winter months. And so this is kind of what the condition of the structure looked like. We see a couple of things here. We see very old, so these are some old patches that were done. So clearly they've had some delamination and spalling and they repaired things. Now these patches are not very well done. We don't see a lot of straight edges, 90-degree angles. These are poor, what we would consider poor patching, so not very good at effectively extending the service life of the structure. We also see patching and adjacent to patching new damage. So something called what we would call the ring anode or halo effect. This is where you have chloride-free concrete next to chloride-contaminated concrete, and that creates a corrosion cell across that boundary. So now you start getting corrosion occurring around the old patches. You can also see that there is a coating on the driving surface, an elastomeric coating. There was also some damage on the underside, so you see some soffit damage. We see rebar corroding. This is an old patch, and we have corrosion in that patch, so maybe that patch wasn't done very well. The wall, we're below grade, so we're seeing water coming through, transporting through the walls, causing corrosion. And then a construction joint here, we see leaking through a construction joint and then corrosion of the reinforcement at that joint. So we were asked to come and do a condition survey of the structure. A couple of things we did corrosion potential measurements, ground penetrating radar, and chloride sampling of this structure. So corrosion potential measurements are where we take a reference electrode and we measure the potential of that reference electrode against the rebar in that structure. And the potential of that reference electrode versus that rebar will tell us the probability of active corrosion. And so here you see this gentleman, he's doing corrosion potential measurements on this wall here. We've previously sounded the concrete, and so we know where the delaminations are. So if we do half cell beyond these areas of current physical damage, we will know where corrosion is active beyond those. So obviously the white hatched out areas is areas where there's physical damage, but we also want to know where corrosion is active beyond that. Because if we don't repair those areas, then in a few years, they're going to have more delaminations and spalls in those areas that will have to be fixed. So here's a corrosion potential survey of the floor in that parking garage. Here's just a small snippet. And so you can see a few things here. The hot colors, the warm colors are areas where corrosion is potentially a high probability of activity. And the green colors are areas where the probability is low. And we see that there's also these gray hatches. Those are where the delaminations are. So those are where delaminated concrete is. So you can see that if we just go out and repair the delaminated concrete, we're not really addressing the fundamental issues of this garage. There's a lot of active corrosion, especially here and over here, where if we don't address those areas, then corrosion is going to proceed. Just so you're aware, so this area is actually the entrance of the garage. So this is the level, the top level, level A. So the levels are lettered, so A, B, C, D, E, and F. So this is where the cars enter and exit the garage. And so right here is where they're where the grade level where the roadway is. So obviously moisture and salts are coming in on tires from the vehicles into these areas. And that's causing a higher risk for corrosion activity. This area over here in the top of the image, this is actually near the elevator bank. This is the elevator. And so in the winter months, they're putting some ice down due to, water and, people's traffic here. So this is where you're getting more active corrosion over here as well. And so with these areas, we can identify where there is active corrosion and then, where there's current delamination with the hammer sounding. Ground penetrating radar, we use that to identify a few things. One is the reinforcement layout. So location of embedded metals is very good at identifying in GPR. We can identify the cover depth of the reinforcement. So the cover depth is really important in understanding the risk for corrosion because chlorides take time to get to that rebar. So if there's a better cover depth, then it might take longer for that structure to deteriorate. And we can also do a qualitative condition assessment of reinforced concrete. So there are chlorides, moisture, and concrete. In the concrete, we can identify if there's chlorides and moisture getting into the concrete or there's deterioration, it'll weaken the signal of the GPR. So here's a typical GPR scan, and you can see these white hyperbolas. These are the individual rebar, and they're nice and bright here, and then they're nice and faded over here. So this is an area of attenuation. These signals are weaker than these signals. So weaker signals identify that maybe there's salts or moisture or deterioration of the concrete occurring here. Now, I can't tell you specifically, oh, there's probably a delamination there, or, oh, it's just moisture and chlorides. GPR cannot differentiate between these different items. It just is affected by them all. So it's really a good tool at identifying where potential areas of future investigation are, right? We know there's something going on here. We don't know what it is exactly, but we probably want to look at it in more in depth. Here's the cover depth survey conducted on the parking garage in Washington, D.C. And you can see that on level D and level C, we have the travel lanes for the garage that we scan. And we can see that in the travel lanes of C, we have a lot more areas of lower cover depth, less than 1.5 inches, whereas with the level D, most of the area is, above 1.5 to 2 inches deep. And so we're going to get better protection to the rebar on level D than we are on level C. And level C being closer to the level on grade, which is level A, there's going to be more salt exposure potentially on level C than D. So we would be worried about the service life of level C versus level D because there's a lot more lower cover on that structure than other locations. Also doing chloride sampling. So here we take in cores from the deck's surface at 0 inches into the concrete section and look at the concentration of chlorides at 1/2 inch increments. You can see here the green lines indicate the solid green is the average cover depth, and then the dotted green lines are plus or minus a standard deviation of cover depth. And then this horizontal red line is the chloride threshold. So at 350 parts per million, the risk for corrosion is high. So if the chloride concentration at the steel depth range is above this red line, then the risk for corrosion is high. And we can see here we have a high surface concentration and then it decreases with depth. And we can see that for several of these lines, if we're 1.5 inches or shallower, the risk for corrosion is quite high. The chlorides are well above the 350 value. Now, if we're at the deeper end of the cover depth spectrum, so if we're closer to almost 2 inches of cover depth, the risk for corrosion is quite low. So you can see that where 1/2 inch or 1 inch of cover depth plays a significant role in the durability of the structure. If we have 1 more inch of cover, the structure goes from significantly corroding to not corroding at all almost. And so that's an important thing to understand. This line here, you can see that increases with depth. This is an oddball. This is most likely what is happening near a crack or some other kind of construction joint where chlorides are kind of getting deep into the structure or moving horizontally water from somewhere else. And so that's an indication that there may be, cracking or a construction joint or some weird defect that's not allowing the proper transport of the chlorides. So based on the condition assessment, we identified that levels A, B, and C were severely corroding. They had delamination and spalling. Concrete had high chloride content and active corrosion. Near the entryway where cars are coming in and out, that's obviously the most exposed. Levels D, E, and F were deeper in the garage, and so thus they had a less exposure to traffic, and they had a reduction in chloride exposure. So D, E, and F had little damage. They were in really good shape because, cars, by the time they get down to that level, there's fewer cars down there. They've kind of deposited the moisture and chlorides on the upper levels. The ramps between each level, though, were kind of corroding because the wheels from cars turning on those ramps had worn off the elastomeric coating, so they had been allowed more chlorides to get in and water into those concrete ramps, and so the ramps were corroding throughout the levels. And so then we look at the deterioration over time and kind of try to understand what's the best approach for preserving the structure. Obviously, we have a do-nothing approach. If the owner does nothing to the structure, it just continues to corrode, right? So here's a little deterioration model over time. You know, we begin that structure is brand new, and then over time we start to have some deterioration. And they went out and done some first repairs, brought the delamination deterioration down to, you know, close to zero, but they really didn't stop or preserve the structure. So that deterioration slope continues on, right? We continue to deteriorate the structure because we only repaired what was physically damaged at that time. We didn't do anything to ultimately slow down or eliminate the deterioration corrosion aspect. So now we're at, you know, this time here where we're at the current state of deterioration where we have much more deterioration than the first time we did repairs. So if we just go out and do kind of repairs normally and do nothing else, in a few more years, we're going to have to come back out here and do a lot more repairs than we did this time. So repairs are just going to keep coming and keep growing. However, we could do a couple of different things. One is we could apply cathodic protection to the entire structure, like effectively do a global corrosion mitigation strategy, bring the corrosion rate down to almost zero, and we're going to kind of flatten out this line. We may have some small repairs to do in the future, but overall, we're going to be fine. Or we could kind of target, be a little bit more proactive, kind of take targeted cathodic protection in certain areas that we need to protect. So based on those half cell potential measurements, say, hey, these are the areas that are actively corroding now. Let's mitigate those areas and preserve the structure. Granted, some other areas of active corrosion may pop up in the future, but we're going to kind of limit those. So we can be much more cost effective here, right? Obviously, basic repairs are the cheapest. Global is the most expensive, but you know, proactive is fairly economical, right? We can take the money we can use, we can apply it to the areas that are the highest risk, limit those areas. We're not going to stop all the corrosion, but we're going to limit the deterioration rate. And so that's going to provide a longer service life for the structure. And so that's ultimately what they did. And so using the corrosion potential measurements, we can go out and locate where we need to apply corrosion mitigation strategy. So active anodes here and stuff. And so while my presentation is not really going to get into the repair side, those will come later presentations that are provided as part of this webinar series. That will be discussed later, but I just wanted to kind of show how the corrosion potential map is used to kind of locate that corrosion protection. This is another project. This is with the Honolulu Club in Hawaii. So this is it was a health and fitness center. So it had a few parking levels on the lower, and then above upper levels were health and fitness center, and the building was going to get reused. So the health and fitness center was shut down, and they're going to kind of remove everything and repurpose this building. And so as part of that, the structural engineer needed to know what the reinforcement and post-tension layout for this structure was, because there were no as-built drawings for this building. So the drawings that existed for the structure were limited. And so the structural engineer who's going to do the reuse design needed to know what the load capabilities of the floor and beams and columns were going to be. So they asked us to come out and use ground penetrating radar to locate where all the reinforcement was so that they could understand the load rating of the structure. And so here, this is the parking level here. These two photos show the fitness levels. And then on the roof, there is actually tennis courts. And so what we did is we brought ground penetrating radar out to that building, and we scanned the floors to identify where all the reinforcement was and what the layout is. So here, the top scan, you can see these are the conventional reinforcement. They're at approximately 16 inches on center. And so we can identify where that horizontal reinforcement or that reinforcement is. And then you can see there's little hyperbolas below that. So this slab is actually post-tension. So we can identify where that layer of post-tensioning is as well, and identify where those bands are. Here's another scan. You can see here's the slab, and you can see again post-tensioning in the bottom of the slab, so we can see what the thickness of the slab is. So here's the bottom, here's the PT, here's some conventional reinforcement. And then we can also see in the slab where an integral beam is, you can see the slab bottom changes. Here it drops down to here. So this is where a beam is. So we know where the beam is, we can identify the thickness of that beam. And again, the reinforcement layout in that beam. You can see here's some conventional reinforcement at the top, and then the very dense reinforcement at the bottom of the beam. And so by using GPR, we can go through the structure and identify where all the post-tensioning is, what the reinforcement spacing is, and provide all this information to the structural engineer. And so here, you know, these areas of yellow are where we've scanned, and you can see where we've identified, okay, here's where the post-tensioning is, here's what the spacing is, even identifying if it's a bundle of 4 tendons, a bundle of 3 tendons, 2, and kind of helping to understand what the existing conditions of the structure are. Another thing we did on this structure is used impact echo to understand the quality of the concrete. So impact echo is an acoustic method where we make an impact on the concrete and it sends stress waves bouncing into the concrete. If the concrete is sound, those stress waves bounce with the full thickness of the slab. If there's a delamination, that reflection will occur shallower. And if there's a lot of cracking in the concrete, we may not get any reflections. And so we have this 4-sensor array that we use to assess the condition of the concrete. In addition to the waves bouncing in the vertical direction, the waves will also travel horizontally. And so we can get a wave speed based on the position of our sensors, because we know the spacing between those sensors. So the wave speed will tell us a lot about the concrete quality. If especially, you know, if there's microcracking, that'll slow the wave down. And so what it will be able to do is identify the in-situ concrete compressive strength based on the wave velocity. And so here is strength in PSI, and then here's the velocity of the wave. And as the wave velocity increases, the strength of the concrete also increases. And so by measuring the wave velocity, we can identify what the strength is in PSI. And so we went through the structure and measured the compressive strength on various elements, on columns, slab, girders, and different things like that. And so we can kind of see what the average compressive strength is here, the deviation, and then min-max. But it's important to know, obviously, that, you know, damage in the concrete will affect this measurement because this is an in-situ measurement. And so, you know, here again, we have, you know, more measurements, you know, we can pull that together. But one thing we can do is look at the compressive strengths before and after removing the damage. And so the table on the top here is the average compressive strength of all of the data points. But then if we remove locations where we saw cracking or damage, so delamination, and we look just at what the compressive strength of the sound concrete is, we see that the average compressive strengths increase. And so here we can see here's what was specified in the original drawings. And you can see things like for, you know, the pool deck. The pool deck was 3,000 PSI, but we're measuring it's around 2,000 with damage. But when we remove the deteriorated concrete locations, we see that in sound concrete, the compressive strength was 3,200 PSI. So when the concrete isn't damaged, yes, it is meeting that 3,000 PSI. But obviously, when there is damage, we're weak. That concrete is much weaker. And so effectively, we can look at what the compressive strength of the sound concrete is, and then also its effect of the damaged concrete. This is a church that we did an investigation on. So this is the roof of the church is supported by these concrete beams and concrete columns. And they were experiencing corrosion deterioration of those columns and beams. As you can see here, you can see that corrosion spalling was occurring of the beams and exposing the rebar, and it was corroding. And the reason for that was carbonation of the concrete. So here's some concrete chunks, and you can break a fresh edge, and you can see here's the corner of the column, and you can see the pink part is where the carbonation is high, and the clear part is where the carbonation is low. And you can see in this image, there's about 1 inch of carbonation of the concrete, you know, here about 3/4, Again, here about 3/4 to an inch. So we're getting about an inch to, 3/4 to an inch of carbonation of the concrete. So if you look back here, that rebar is very close to the surface of that concrete. So if the rebar is very close to the surface and you're getting carbonation of that first inch of concrete, it's going to cause corrosion of that steel and then spalling of the concrete. So then we went and did corrosion potential surveys of the columns and beams and identify where those areas of active corrosion are. And you can see the yellow, the highlighted areas. These hot colors are indicate where carbonation is a problem, and they're going to have spalling of concrete. This is a project in New Jersey. This is 150 Bay Street. This is an apartment building. The apartment building is comprised of reinforced concrete with brick masonry infill. And so there were spalling of the concrete that was occurring and falling off the building. And so the owner wanted to preserve this structure for the long term. So one of the things we were asked to do is kind of evaluate the structure, what was the corrosion problem, and then kind of, develop some rehabilitation solutions. One of the things was they didn't know the reinforcement pattern. So using ground penetrating radar, we went and looked at the concrete and kind of laid out where the rebar is. So obviously just, kind of some examples here. You can kind of see where this lintel beam is. You can see there's one rebar across and a couple of vertical. You have the columns here with some vertical and then a beam here with several horizontal rebar. So we can go through that whole structure and identify where where the reinforcement is, so we know how to design a corrosion mitigation solution. Did some chloride sampling. This building is relatively close to the water, so you might get some atmospheric chlorides off the water. You can see obviously the chlorides are much lower, but there is still a little bit of chloride in the concrete. Here's that 350 line. You can see most of the samples are well below it, but we do have some exposure. One high level, so this is probably near a crack or something where chlorides have gotten in from the air. But the real main issue is carbonation of the concrete. You can kind of see here where the where the pH is high here, but then the pH is low here, and then this is a rebar that's corroding. And so carbonation was occurring in different areas of the structure. And the carbonation was actually very spotty. So, we broke a fresh area over here. There was some corrosion here, but there was also area nearby where the pH was kind of high. So, but you see that the carbonation is not uniform on this structure. Kind of depends on the concrete quality at the time of the pour, the aggregate distribution, and things like that. So on this structure, due to the age of the concrete, the carbonation was occurring kind of not very uniform, and so different areas were corroding at different rates. This is a building in Naples, Florida. This is a condominium here, and you can see it's built out actually on the water on reinforced concrete piles. So while this is a building, it's almost like a pier structure because it's effectively built on piles out on top of the water. And so this is in Naples, so it's Florida, so you've got salt water here. And you can see that, the piles are obviously corroding and deteriorating in this area. So we were asked to kind of take a look at this structure. You can see we've done some hammer sounding, identified delaminated concrete. Here, where we've chipped off concrete, we see clearly rebar is corroded and broken. And so these piles are in need of corrosion mitigation. And so here we've done, this is some columns that we measured the corrosion potential measurements, and you can see where we've identified the active corrosion on each column or pile, and you can see where the delaminated concrete by these hatching marks is where the delaminated concrete is at. And so by going through all those piles, we could classify which piles were actively corroding and which piles needed to be repaired or preserved for that structure. This is a post-tension parking garage. So this is a post-tension tendon that has failed. So the parking garage, there were several locations where PT tendons had failed, and so we were asked to come out and do some evaluation of the corrosion of these tendons. And you can see here's the elevation of the garage. Pretty basic, precast slabs with post-tensioning and a steel frame. So unbonded post-tensioning in parking garages. So they don't have quite, the level of protection you would think of like rebar, right? So these are strands in plastic sheaths that have grease inside to protect them from corrosion. However, breaks in the sheath or not properly done anchorages allow water or chlorides to get into those strands and can cause corrosion of that strand and eventual failure like this. And so here is some of the examples of the condition on the structure. So you can see here's what looks to be a previous patch was done, but you can see a spall has occurred where the tendon is exposed. Here's a corrosion spall. Again, you can see two tendons here, two monostrand tendons are exposed in that spall of the conventional reinforcement. Here's the anchorages of the tendons, and you can see obviously there's a concrete spall here. The anchorage caps are gone. This allows the strand to have moisture and exposure here. Here is an anchorage, and you can see moisture transport through the anchorage. So obviously we have moisture and grease coming out of there, so that's an indication that there's water along those tendons. Because this is precast slabs, there are joints between the slabs, and you can see there's water staining occurring there, so there's water transport between those slabs. Which can allow for water to get into the post-tension sheathing as well. You can see here's actually water just running off of the through those joints and dripping through those joints. So, water getting into these strands is a major problem for this parking structure. So one of the tests that we do is post-tech corrosion evaluation. So what we do is we make a port on either side of the tendon. We push dry air into the port, and then we measure that dry air coming out and measure the RH and temperature of that air. And if that dry air is picking up moisture and we measure that out here, then we know that, the tendon is potentially wet or has a risk for corrosion. So here is some results of that testing. So here we have, the temperature and the relative humidity of the air coming out of those tendons. And you can see here's kind of above this red line, the tendons are considered very wet. In here, they're kind of wet, dry, they're moist, and then below the green line, they're dry. These three dots, where they're at 100%, that's where, there's just standing water in the tendon. So you can see here, we've put pressure on this tendon and water is just spurting out of the duct, and here water is coming out of the anchorage. But then you can see, definitely, 70 to 90% RH is coming out of those tendons. So there's a lot of moisture along those tendons. Another test that we can do is, do some openings and then check to see if the tendon is still under tension. If you can fit a flat blade screwdriver between the individual wires of the strand, then that's an indication that the strand is no longer under tension, and that's called the screwdriver penetration test. This is a parking garage of post-tensioning where they wanted us to test what the tension is of those strands. So what we did was a lateral pull test. And so what we did is we opened up the concrete, we connect a load frame and a load sensor, and we pull those strands laterally. And the amount of load it takes to pull them and the deflection will tell us what the tension is in those strands. And so here, here's some openings. And so here you can see the strand right there. There's another strand right there. And we hook the load frame up and we do a couple of tests and we pull it with a certain load and we measure the deflection. And based on that, we can calculate the tension in the strand. And so with the tension in the strand, we can determine if the strands have been tensioned properly or if they've really, and so you can see here, some of these strands are not tensioned quite to what they should be, especially this test 4 at this tendon, clearly not enough, not load on that tendon. So we were asked on that structure to go out and verify that everything was tensioned properly. Another structure that's post-tension that we looked at is at the Kansas City airport. This is a shell structure. So right here's a shell structure, and then right here is a shell structure. So these are two airport aircraft hangars, and they're quite large. They can fit like 3 airplanes in each of these hangars. And you can see that there's a ridge in the roof. And so this structure is actually post-tensioned in 2 directions. So the roof is post-tensioned in this kind of across direction. So perpendicular to that ridge, the roof is post-tension. And then this arch here is actually post-tensioned in the underneath in the basement of the building. It's post-tension. This is almost, think of this as like a bow and arrow. So effectively there's post-tension in the basement to keep tension or keep compression in this arch. And so the post-tension cables in the basement give this arch its shape. And so we were asked to do an evaluation of those tension cables. And so here's what it looks like in the basement. So you have in each of those two buildings, there's this beam that has 12 tendons. So these are 12 anchorage ends. And in each anchorage, there's 34 button head single rod wires. So here's a little bit clearer image of the anchorage cleaned. You can see that there are 34 wires that are post-tension in each anchorage. And so that applies the stress in that arch to keep the structure, to give it its shape. And there are these grease boxes here that are applied over these tendons to keep them from corroding. But because these structures are below grade, there is a risk for water getting in there. And we were asked to kind of look, is there a risk for corrosion on these strands? So one thing we looked at, so there were a couple of broken wires sticking out, and we pulled those out, and you could see that there were some failures of the strands. Looks, kind of not really a corrosion failure. May have been a failure during during stressing. So one of the things we did was we did load testing. So we did a lift-off test. So we applied a jack at each anchorage, and we pulled the anchorage off. And when we applied enough load that the anchorage came off off the bearing plate, then that told us what the tendon load was. So how much stress was in the tendon. And so here's the load jack that we used. And so effectively here you can see here's the jack pressure in PSI. And then, we got lift off. We converted that to how much load in kips we had. And so based on some original drawings, we knew what the load of those cables should have been. And so we can effectively understand what the effective number of wires still is in that, if there's potentially broken wires. So the expected load of the cables was supposed to be around 245 kips. So each anchorage should have had about 200, or each tendon should have had about 245 kips on it. And so if we saw loading less than that, then we knew we potentially lost a few wires, or, there's some relaxation. You can see that tendon 11 only lifted off at 194. So potentially there's almost 7 wires broken. So, the effective amount of wires in that cable is only 28. So we were able to go through and identify, what the effective load is on each one of those, and where, how many effective wires there are. One thing we also did was look at, is there moisture in these tendons? And so what we did on the opposite side at the other anchorage, we put pressure onto the, so they have greasing ports. So they have a little greasing port that we connected onto, put pressure onto it, pushed air across, and we can see that there is dripping water coming out of these anchorages. So as we put the pressure on, we were pushing water out from the other side. And so I'll replay this video here, but you can see dripping water like down here, there's some dripping water. And so that's so effectively water is getting into these anchorages. Even though they're well greased, water is still getting in there. And so that can lead to corrosion of those cables. And so obviously protecting these cables from getting water infiltration is really critical in their durability of this structure. With that, I'd like to thank everyone for watching this webinar. Up there is my contact information. So if you'd like to ask any questions of this presentation, or would like to know anything more, please don't hesitate to reach out to me directly. I'd be happy to answer any questions that you may have. So with that, that's the Preservation Alliance webinar on the evaluation of parking and building structures. There are other webinars on other aspects on repair strategies and things like that. So please stay tuned to those future presentations. Thank you.